Hello and welcome to our webinar, Visual Exploration of Trajectory Data. My name is Brendan Williams. I am the Research Program Administrator at Portland State University's Transportation Research and Education Center. TREC leads the National Institute for Transportation and Communities, one of 7 national university transportation centers funded by the U.S. Department of Transportation. NITC's research priority is improving mobility of people and goods to build strong communities. NITC consortium members are the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and Oregon Institute of Technology. I enjoy having a role in connecting our researchers to you, our audience. I am organizing this webinar from home. If we have any problems, please bear with us for a few moments. Our presenters today are Dr. Nikola Markovic, Seth Miller, and Dr. Mark Franz. Nikola is an assistant professor of transportation engineering at the University of Utah. His research focuses on visual analytics and operations research. Previously, he worked at the University of Maryland's Center for Advanced Transportation Technology Laboratory, the CATT Lab. Seth is a PhD student in civil engineering at the University of Utah. His research is focused on data science and spatio-temporal modeling applications in transportation engineering. Mark is a lead transportation analyst at the CATT Lab. He is developing and improving online transportation performance measures, analysis tools, and visualizations for public and private sector clients. TREC has some upcoming events this Friday, April 10th, starting at 11:30 a.m. Pacific time. We'll have a webinar presented by Hoonwei Dung from Cal State Fresno on moving toward equitable transit-oriented developments by integrating transit and housing. Our Friday transportation seminars are typically in person and online, but due to the COVID-19 pandemic, they are exclusively delivered online. Our next NITC webinar is on May 12th at 10 a.m. Pacific time. Connected Vehicle System Design for Signalized Arterials, presented by Dr. Xianfeng Yang from the University of Utah. Okay. A brief overview. The presentation will be about 40 minutes long. Then we'll have about 15 minutes to answer audience questions. During the presentation, please submit your questions via the GoToWebinar control panel. If you have a question specifically for one of our presenters to answer, please state, this question is for Nikola, Mark, or Seth. After the webinar, you will receive an email with the link to the video recording and presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. Instructions on how to redeem the credit will be included in your post-webinar email. With that, I'm going to hand it over to Seth.
Hello, thank you for the introduction. I'm going to be talking about some trajectory data. I'm going to briefly cover a model I used to process the trajectory data just to provide some context for the visuals, but the visuals will of course be the highlight of the presentation. You can see on this slide our website. If you go to that website, you'll be able to access many of the visuals that are in these slides. So this is NREX trajectory data, and these visuals show NREX trajectory data, and the image on the bottom right specifically shows waypoints for a single vehicle. What a waypoint is just a location at a particular point in time. When we aggregate the waypoints, we can see large trips moving in Utah. This is 2,000 trips. It's just a small sample of the trips that INRIX has provided us. But when you plot all the waypoints, you can see really how extensive INRIX data is. We actually have trips going all the way from Washington through Oklahoma, Texas, and so forth. And INRIX is actually the only company that provides full data trajectories. There are other companies that will provide the counts on particular roads. Excuse me. They'll provide origin destination counts, but they don't really provide you with the data that you would need to see what demands there would be on a road network given a particular origin and destination. So another set of data we used for our analysis are sensor stations. These were provided by the Utah Department of Transportation. We had 298 across the state. This visual on the right shows the penetration rate, which is really just the percentage of trips that INRIX is able to capture. And between stations, we have between 0.5% penetration rate and 13% penetration rate. After we pre-processed some of the data, we created some visuals just to verify that our pre-processing was done correctly. The visual we're looking at here shows variations in traffic density over time. You can see right here where we're in the middle of the day, the I-15 corridor running along here and the 215 belt route are areas where there are a lot of travelers. And as we go later in the night, we see the whole road network becoming blue, indicating that there are not very many people driving at night, which is exactly what we would expect. Now, this visual is available on our website where you can actually see kind of the fine details about it. But for this presentation, just think about the size of the bottom area versus the size of the top. The bottom shows the trips going to Salt Lake City, and the top shows the trips exiting. And we can see that the bottom will actually grow in the morning, and then it will shrink later in the day. So right here, it's roughly equal because it's the middle of the night, but we're soon going to reach morning rush hour, and you're going to find that the bottom will get very large. This indicates people are commuting to Salt Lake City for work. It's one of the most commuted to cities for work. So this verifies essentially what we expect from the data, that people are traveling to areas for work in the morning and then leaving home in the afternoon. So one of the caveats with the data we've processed is that we only have a portion of trips, and there are many things that would be useful if we had the whole population of trips. We could calculate average annual daily traffic, and we could also look for the whole system, what types of delays are we seeing at different points in time. We can analyze it during holidays, we can analyze it during, say, a special event, and then of course we can see information that's helpful for verification for Map 21. One application that's particularly useful to UDOT is they don't currently have any ATR stations on the Mountain View corridor. This Mountain View corridor right here is going to be turned into a freeway over the next 30 years. It's part of the UDOT 30-year plan, but they're not actually able to see as detailed of information for people traveling on the roadway and accessing the roadway as they would be able to see if they were using trajectory data. So we proposed a fairly simple method, and all you have to do for our method is essentially add a new column to INRIX data. So there's nothing too really complicated for anyone who's trying to take our scaled trajectories and apply them. What we do is we say a particular trip will have a scaling factor, and that means a trip will represent a particular number of trips. So we generate a table with origin, destination, and classes of departure time, and we will take an example trip. We'll take the origin, the destination, the departure time, and we'll look up on the table, and we'll update our new column with the entries we look up on the table. we compare our model to a model from MIT. This model has over 350 citations. It's a very well-known model, and we just compare it as a baseline. So for people who don't have much experience with math, or with mathematical optimization, don't get lost in this notation. Just pay attention to these 5 callouts. Our model has 5 components. We try to estimate the counts crossing those stations. We need to decrease overfitting, and we introduce a parameter where we're able to control accuracy or overfitting. And of course, we estimate the counts using the scaled trajectories, which is just essentially summing up all the trip counts for the origin, destination, departure time combination. And we also tie our rates to a system-wide penetration rate so that we can make sure that our values don't go into ranges that we wouldn't expect them to. So we split our stations into 2 different groups, one for testing and one for training, so that we could get a less biased estimation for when we validate our model. Again, if you're not really familiar with a lot of these modelings, don't worry about the cross-validation. This is more or less just for people who are more familiar to take a look at it and see how we cross-validated our data. And these visuals here show the error both of our method and the baseline method. And you can see that we've substantially increased the performance. This graph right here, the error on testing data, is really the most important plot, and it actually shows that for pretty much every location, we're actually outperforming the baseline model. So after we processed our data, we made a visual tool to verify that our origin and destination counts were scaled properly. This visual is also available on our website. Here we have Salt Lake County highlighted, where you can look at the thickness of the bands in this chord diagram, and you can tell what the most traveled to and from counties are. So here for Salt Lake, roughly 1/4 of the trips involving Salt Lake County that leave the county are going to or from Utah County, and then another 1/4 are from Davis County. This plot on the left, we see the number of trips entering Salt Lake County. On the right, we see the number of trips exiting. And you can click on any of the bars to highlight particular areas where you want to see the origin and destination counts. So the methods we used to process this data can be taken and they can easily be transferred to other places. So we could easily take any other state, find the same analysis, and we can of course also redefine our origin and destination combinations. We used counties in the previous combination, but we can of course use those for TAZs, zip codes, cities, and many other things. So I would like to acknowledge some of our partners for this project. Of course, NITC, they provided the funding for the project. NERCS provided the trajectory data, and UDOT provided the ATR station counts. Now, if any of you have questions, feel free to ask them in the chat, and I will try to answer them during Mark's presentation. Mark will be following me. He's from the Center for Advanced Transportation Technology Laboratory. They offer visual tools, and their visual tools are ones that can easily have our data as input, and they can also have other forms of data as input because they're data agnostic. So I would like to turn the time over to Mark to talk about the work that he's doing in the CATT Lab.
Great, thanks so much, Seth. I'm gonna change the presenter to Mark. If you have questions for Seth, please ask them anytime now. But we will be answering them as an organized Q&A at the end of Mark's presentation. Thank you.
Well, thank you, Seth and Brendan, for the introduction. Just a quick AV check. Can you hear and see my screen?
Yeah, we can.
Yes, Mark. Yes.
Okay, great. So yeah, thank you for the opportunity to present today. As based on the introductions, I was a colleague and a PhD student with Nikola at the University of Maryland. I stuck around at Maryland to work at the CATT Lab, as Nikola did at first. He's now at Utah, which is how I got connected to this group. So I appreciate the opportunity coming from the East Coast to present to an audience that may not know as much about the CATT Lab as others do. So again, my name is Mark Franz. I'm the lead transportation analyst at the Center for Advanced Transportation Technology Laboratory, also known as CATT Lab. So in my brief time today, just kind of want to highlight and give an overview of some of the tools and the ongoing research at CATT Lab related to the visualization and analysis of trajectory data. So what I'll do today is just have a brief background on the data itself, kind of supplementary to what Seth was talking about. I'll go through hopefully some live demos of our online tools that are analyzing trajectory data for some of our state and city DOT partners. And then as time allows, I'll talk about some of the ongoing and future work that we're pursuing at CATT Lab related to trajectory data and just general human behavior patterns. So one thing that I think often gets mixed up is some terminology when we talk about trajectory and OD data. Even though they're related, they're not 100% the same. So origin destination data is just that. It has information about the departure time and the start location or the trip origin. And the supplement to that is the time of arrival at the destination. So you have just the origin and the destination data. Well, that data is incredibly useful. It doesn't have any details about things like specifically what route is taken or different modes that they can be imputed based on the travel time between nodes. But when we think about how we visualize raw OD data, this is a traditional map where you see the node and chord chart overlaid on the map so that you can see the various patterns, in this case, between cities and the Rust Belt. Now, trajectory data, not only does it have the origin and destination information, and as Seth mentioned, it also has some pretty rich information that we call waypoints. I've also heard them called breadcrumb data. Essentially, it's whatever the device, the location-based service device. It could be a traditional GPS system, an in-vehicle GPS system, connected vehicles, or cell phone-based. And essentially, every couple of seconds or up to a couple of minutes, depending on the data provider, you'll get a ping, which creates that waypoint, which in its most raw form is a lat, longitude coordinate with a timestamp. So it's a relatively newer data set that the transportation industry is starting to wrap their heads around and finding ways to utilize that to better understand travel behavior patterns. So when we look at how that data looks different, here's what true trajectory data looks like. So point 0 being the origin of this trip and point 14 being the destination, with waypoints 1 through 13 in between, so that we can use those waypoints to kind of reconstruct the route and the travel time for the full trip, not just on one particular segment, which has traditionally been done in legacy probe data. So there's a lot of, obviously useful and new information that we can learn from this new data set. Of course, the challenge with this data set is that it's pretty big. It's one of the bigger transportation-based data sets that I've worked with. So when we built our tools at CATT Lab, we started with just a 4-month sample. That included any trip that has at least one waypoint in the state of Maryland. And that alone, that 4 months of data in Maryland, which geographically isn't a super big data set. We had 20 million trips with 1.4 billion waypoints, and it was 112 gigabytes of data. And that was sort of what at least I call raw data that we get from the various data providers. It's that flat longitude with the timestamp. And again, in its rawest form, as shown on this graphic, the original waypoint may or may not fall directly on a road map. So what you have to do is do some processing of that data to get it onto the road map. And then the other part that you have to do, we call that step snapping. So you snap the waypoint to the road map. and then you do the routing. So like I said, it could be a few seconds or it could be a few minutes in between the waypoints. So the snap waypoints are green, and then we do the routing to figure out what's the most likely route taken between those waypoints. So when you're on an interstate system, it's probably pretty obvious that the person just stayed on that interstate between waypoints. But it becomes a bit more challenging when the temporal resolution of your waypoints is 2 to 3 minutes, and you're trying to figure out how they traveled 6 blocks in downtown Manhattan. So we have to come up with ways to take to process that data so it's usable in the analysis. So this is 2 general processing steps are needed called snapping and routing. So obviously the benefits of trajectory data is that you get, depending on the data provider and the temporal and spatial coverage, you're going to get these pings on every road just about that you're probably interested in understanding travel behavior patterns on. So major and minor roads. You can get some continuous updates of this data for travel behavior patterns. So if you want to look at seasonality effects, if you live in an area where more people might be visiting a park or a beach area, this data is very useful for helping to tease out real world observations that it doesn't have to be specifically modeled as it has in the past. And then there's other applications which I hope to highlight here for both planning and operational analysis. So as I mentioned, the CATT Lab, and again, for those who aren't familiar, at CATT Lab, we're in theory an academic research lab at the University of Maryland Civil and Environmental Engineering Department. And even though we do go after traditional academic activities like research proposals, we operate more like a consulting firm where we have contracts with, I think, 40 state and city DOTs at the moment to help them fuse and ingest their data. So we're in the business of helping public agencies bring in data and with a few clicks of the mouse generate some metrics and results that they can use for both planning and operational decisions. So with that in mind, we saw the opportunity to build a suite of online tools for us to help our agencies and researchers alike analyze this data. And we have 3 general functions within our trajectory analytics or TRIPS analytics suite of tools. It's the OD matrix, which I'm going to demo each of these, our segment analysis, also in the planning world, I think that's called select link analysis, and then our route analysis tool. So I'll kind of go through and jump back and forth between my PowerPoint and my web browser to give you the live demo. So OD matrix, so just quickly, you can use this to validate or calibrate planning models. You can use this for supporting traffic demand management decisions and policy changes, updating transit services, you name it. There's a lot of different applications you can do with this. So I'll jump out of my PowerPoint for a minute to show you the demo here. So this is what our landing page looks like. As I mentioned, we're working with a few different agencies currently at CATT Lab, and you can see the various data sets that are available. For the purpose of this demo, I'll focus on Maryland because it's the roads that I'm most familiar with talking. So let me show you the OD tool. So after you select the data set, you come to the tool page. I'll select OD matrix. So there's 2 different options for creating the matrix. You can create a traditional matching axis where the origins and destinations are the same, which is the one I'm going to build. You can also create a matrix that has custom origins and destinations. So I'll just show you what that looks like without generating the results. But a use case here is maybe I wanted to understand, I wanted to do parking management in downtown Baltimore. So I can select a few of the surrounding counties, Anne Arundel and Baltimore and Howard County are ones that are nearby. And I want to know where these people came from, where they park and at the TAZ level, the traffic analysis zone. So I can pick a subset of those, and you can see my origins would be my trips that left the county surrounding Baltimore, and then those trips completed within the traffic analysis zones where I wanted to better manage my parking, for example. But in any case, what I'll do is, I will create this matrix using the county level. So I'll mention that all of our tools by default spatially aggregate the trips within the data sets that we have. By default, we use county, sub-county, and traffic analysis level from the Census Bureau, but we do have the ability to switch out one of these geographies based on what our agency partners want. So if they have their own custom traffic analysis zones, for example, that they use in their planning model, they can send us those geographies in a shapefile, and they'll become available for them to aggregate these trips. In any case, I'll go ahead and just select all the counties in Maryland for this demo. So again, the origins and the destinations are symmetrical, the matching axis. You get a preview of that matrix, and then if that's indeed what you want to see, you hit generate matrix. It'll take a few minutes here to crunch through the numbers, and it'll generate a matrix which you can interact with and apply different filters. So by default, the output of the matrix shows the percentage of trips between the OD pairs. Everything here is dynamic, so you can slide around the color schemas to highlight certain cells. In the state of Maryland, we have, as I mentioned, the first 4 months of 2015 is what we built our tools on, but since then they've purchased the full calendar year of 2018 and 19, which is available. And if I wanted to filter by specific hours of the day, say the AM peak period, you can just play with this time wheel. So now I'm looking from 6 to 9 AM, and by clicking outside of it, it'll reprocess that data, applying the filters that I just selected, and it updates the table accordingly. The thing that's interesting about this particular data set is that this data set for Maryland is from NRICS, but again, we can ingest data from any data source. But they also give the ability to break down by vehicle class. So we have light, medium, and heavy vehicles. So if you're interested in looking at just commercial or passenger vehicles, you can turn certain filters off and on to update the matrix based on that consideration. We also have the ability to switch between not just the percentages, but if you wanted to look at the average daily counts or the total counts, you can simply click on that here and then click outside, and then you get the raw number of vehicle trips. In this case, I've filtered for light vehicles, so these are mostly passenger vehicles, often commuting trips that we see in the matrix. And then again, because this is a symmetrical matrix, there's another way that we can visualize the data, similar to what Seth and Nikola presented a few moments ago with the Chord Chart. This shows the top 10 OD pairs, again at the county levels what I've selected, and you can interact with the list, which highlighting that county will dim down the other chords on the Chord Chart, as you can see, or you can go to the Chord Chart itself, and it'll only show the chords that are relevant to the county that you're hovering over, with obviously the thicker chords representing more trips between that origin and destination pair. The next tool, and I have some screenshots here just in case my internet was too slow to do the demo, is this segment analysis or select link analysis tool. So again, this can be used for model validation. And the way that this tool works, let me give a brief description, is you can use the tool and go in and select a road segment or collection of continuous road segments and identify where those trips started from and ended. So you can use this to look at the effectiveness of dynamic message signs or other traveler information systems. If there's a major crash and you put up a VMS or a DMS sign and want them to take a detour route, you can use this type of tool to do a before and after study on how effective that messaging was. You can use it for planning, integrated corridor management studies, and the list goes on. Lots of different applications for applying this select link segment analysis tool. So again, I'll go back to my browser to do the demo of it. So I pre-ran this query. It takes a couple of minutes depending on the size of the data that you're requesting. But essentially the way that the tool works is you can select a road segment. In this case, I selected I-270 in Maryland. And I'll zoom in here and show it to you because when you're zoomed out, it's hard to see this one segment. So it's this green segment that's here is the one that I've selected. It's one of the top bottlenecks in the state of Maryland during the AM peak period as it connects the northern counties in Maryland to the Capital Beltway, which is this ring road that you see around, which provides access to employment centers in Northern Virginia and in Washington, D.C. But in any case, I've selected this one segment, so it's a 1 mile or a 0.89 mile segment. And again, I've requested the data to be aggregated at the county level. It could also, as I mentioned, be done at the sub-county and TAZ if that was desired. And essentially what it's showing right now is the difference between origins and destinations at the county level. So the more blue colored counties represent that there's more destinations. And because this is a southbound segment, that sort of makes sense, whereas we use shades of orange for the origins. And I can also look at each of them independently. So if I want to look at just the origins, it'll get rid of the blue and just show me the origins on this map. So as you can see, as I mentioned, the way that this data was generated from NRIX on behalf of the Maryland Department of Transportation includes any trip of a waypoint in the state of Maryland. So for this selection of data, you can see that some origins started as far as Chicago and upstate New York that ultimately used this road segment. I can also interact with this map and display by turning off the various bins that I have. I'll zoom in and I can show data labels for this particular county, Montgomery County, Maryland, that use that segment. We can also switch to the destinations alone. I'll turn the data labels off because it can be overwhelming when you have everything displayed. And again, you can see the spatial coverage here, the trips going as far south as Alabama and South Carolina in this particular data set. As before, we can also, I didn't request this, but you can turn on different filters if you want to look at passenger or commercial vehicles. And then the same thing with the time range here, I've selected just weekdays, again, from 6 to 9 a.m. And I'm just using 2019 data when I pre-ran this. And of course, all this data and the visualizations can be downloaded and used for communicating to people within your agency or to the general public. We try to make these so that the visualizations are mostly intuitive, hoping that it can help meet the needs of our agency partners. The third tool that we have available is our route analysis tool. So the way that this tool works is that it allows our users to select an origin and destination pair and then discover the routes that are used in between that origin and destination pair, and also provide statistics not only on the split of trips between those routes, but also, when possible, provide statistics on the travel time and travel time reliability. So of course, many use cases, and again, everything that I'm showing is from the same data set that you can get for trajectory data. So model calibration before, during, and after analysis when there's a work zone and you're getting people potentially to change their routes based on that for detouring. You can analyze the impacts of a toll lane if people are jumping off of the main line to avoid the toll and use side streets to get between origin and destination pair. Look at providing accessibility to critical services like hospitals and employment centers, and the list goes on. So our route analysis tool, I've also pre-ran this. Again, it takes a few minutes to crunch the numbers here. But essentially what I did, again, in the state of Maryland, I picked 2 counties, Frederick County, Maryland, which is shown in orange, and then Prince George's County, Maryland, which is where University of Maryland is. This is an interesting use case because about 10 years ago, they opened up a toll road that people can use from this part of northern Maryland to provide access to the Beltway. And we're able to tease out information on how commonly that route's used. So it's actually not the first route. This is I-70. Then they're taking the Baltimore National Pike southbound. So you're seeing the #1 ranked in terms of the number of trips. There's 24 trips here, so that #1 represents, in the circle represents the #1 rank. I can also show other routes. So the #2 ranked route is in fact the inter-county connector. So that's the toll road that I was mentioning. So people come down I-270 and then across eastbound to access Prince George's County. And then the #3 ranked trip is they go all the way south onto the I-495 Capital Beltway. So I'm sure that not everyone on this call is familiar with the travel patterns in the greater Washington, D.C. region, but this sort of jives with what you would expect in terms of the split between trips and things with travel time, with one of these being a toll road. People might not use it as their first choice if they don't have to, but it can provide benefits for those who can afford that toll. And again, this type of information shows, some really never been able to be done before a few years ago outside of the modeling world. So we have some real world observations about how we can better assess the origin and destination, as well as route analysis usage between particular origin and destination pairs, which is pretty exciting. So these are, again, just visualizations I took screenshots of. So one tool that we actually just launched yesterday, the timing of this webinar was very convenient for that, was an intersection analysis tool. So for this particular tool, it's still utilizing trajectory data, but it's filtering it out. So we only have the very high temporal resolution data to do signal analysis to estimate things like arrival on green, queue length, delay incurred for each turning movement. So it's an interesting, more zoomed in level type of analysis. And again, for those who on the call are familiar and experienced with doing signal analysis, it's traditionally to go out and collect real world data for this takes pretty significant effort and money to do turning movement and travel delay. So this data source offers a potentially groundbreaking paradigm shift in how we can analyze intersection performance from a third-party provided data set. So this is a screenshot of the tool. Again, I'm going to jump out one more time because this just went live yesterday. And again, I pre-ran this query, but essentially what the query page allows you to select one or multiple intersections, and the output will show you this table, which ranks the intersection movements by, in this case, by default is percent arrival on green. But if I also want to look at the volumes, the vehicle count, I can click on that and it'll re-rank based on the column that I click on in the table. So percent arrival on green is the one that I'll leave it on. So we show, by clicking on that particular movement, we can see that movement on the map, the segment that we're including in the analysis in terms of counting as travel time. So over 50% of the vehicles are arriving on green here. In addition to the map-based representation, we also have the intersection breakdown schematic, which is showing and highlighting, in this case, the southbound movement, providing information on the arrival on green with all of the other associated movements at this intersection shown next to it. So that's a new one that we just launched, and it's currently using data in the Detroit, Michigan area. It's one that we're pretty excited about. So with the remaining time, just kind of want to go over some other ideas that we have related to further utilizing trajectory data and cell phone-based, location-based services data. So an enhancement to our route analysis tool, as you might imagine, there's a lot of different routes depending on the geographies that you can select that can be shown. So what we're doing is developing functionality to create a screen line. So if you want to go in and focus and filter for trips that cross or use only specific routes. So in this particular instance, you can see that routes A and B that are shown, or the screen line points A and B show two routes that start, they leave the origin county at different points, but ultimately merge together somewhere south to go to their final destination. So if you want to know what the split of trips were before they merged together, the screen line tool can provide pretty valuable information before that merging point, showing that in this case, 81% of the trips that ultimately end up on the blue route labeled as number 2 came from the blue line across point B, where the other 19% crossed through point A in that case. So again, start with kind of a bigger view of the data, and then providing tools for the users to go in and zoom in and drill down and get more specific information and let them explore and discover new insights from the data. So that's an enhancement that's currently under development within our route analysis tool. And of course, by hovering over either one of those points, you can get more detailed information about the travel time, the min and max, and the reliability of the trips, travel times of those trips that use that particular route. We're also working on some functionality to support chord inner boundary analysis. So there's some commonalities with the screen line idea, but here the user would come in and select a geographic study area. In this case, I use Frederick County, Maryland as well. Applying the same filters as you can with our other tools, day of week, month out of the year, and time of day. You can also filter by the vehicle type, light, medium, and heavy. And essentially what this tool does is, rather than show you originally the true origins and destinations of trips that cross this boundary, it just shows you the entry and exit points. So each of these dots would represent the ingress or egress, entry, exit points for the geography that you've selected, with the inbound arrows representing the trips that entered and the outbound arrows representing trips that left. And this 34 would be representing internal trips. So essentially, when we create this boundary, as you can see on the table on the left here, there's 4 general trips that can be made. There's internal to internal, internal to external, external to internal, and external to external, which are your pass-through trips. And essentially, by creating this tool, we're hoping that we can allow users to, with a few clicks of the mouse, explore and start discovering those types of trips. And then if the users do indeed want to see the true origins and destinations, not just where the crossing points were, they can go in and click on each of those entry or exit points and select the type of trip they're interested in. So in this case, the user selected, I'm interested in looking at the external to internal trips that cross this point. So we're able then to show the origins of those trips that came in to that point. So again, this is another feature that's currently under development, hoping to have it out soon. Then lastly, this is my last slide. Just wanted to mention kind of a timely research project that we're doing at CATT Lab, along with our partners at the Maryland Transportation Institute and some other professors at the University of Maryland. Is we're looking at utilizing cell phone data to analyze and gain insights on if people are staying quarantined or how far they're traveling, how their trip patterns are traveling in terms of, we know obviously not as many people are commuting now. They still might be traveling just to get to the grocery store or to the pharmacy. So we're creating a dashboard now to help us link up this travel behavior pattern from cell phone-based data. And we're working on linking that to where there is reported cases of the COVID-19 virus, so that we can help communicate this not only to our transportation agency partners, perhaps more importantly to the medical community who's trying to gain insights on if these policies that governments are imposing for people to stay at home as much as possible are effective in terms of mitigating the spread of the coronavirus. So this is one that we're working. We're hoping to launch it in the next couple of days. It'll be open to the public and to public health officials, so that they can potentially use this to better understand the effectiveness of the policies for stay at home. So that concludes my presentation. I will go back to my portal here to see if there's any questions or comments. I do appreciate the time for allowing me to present the research at CATT Lab. Thank you.
Thanks a lot, Mark. So yes, audience, if you have questions, please submit them now. We have until 11 to handle them. Just like to check in with Nikola and bring this back to the research project. And Nikola, I know that you were able to work with UDOT and present the data back to them that you had received from them in this GPS trajectory data. Can you talk about that?
Yeah, sure. So the whole objective of this NITC project was basically to acquire NRIC trajectories and then show it to the agencies. What is it that we can possibly do with this new and exciting source of data? So we had a number of meetings with UDOT. So we demoed some of the visualizations that Seth has presented, and they seem quite excited about it. So we're hoping that down the road we'll be able to get some projects from UDOT where we'll be able to get more of this data and then try to streamline for them some of the analysis that they're interested in.
Great. So Seth, we have a number of questions for you. You've handled some of them. We have one that just came in regarding resampling using the INREX data. Can your model only estimate the aggregate volumes, the OD matrix, or reconstruct the individual vehicle trajectories?
We reconstruct individual vehicle trajectories.
Wonderful. Yeah, and would you like to just maybe address any of the questions that you were answering just recently?
I believe the answers I typed out answered all the questions. Let me look through here. One question applied to both Mark and me. The question was if we have examples for public transit. For our analysis, we only used vehicles. So we have scaled trajectories for buses, but we haven't created any visuals to show the bus routes or anything.
Okay. So another recent question, how long does a vehicle need to stay to be considered a destination of a trip? There is interest in OD data for travel, but worried that gasoline or restaurant breaks interrupt true OD pairings.
I can actually try to answer that question. So this is actually a good question for NRICS, but based on our understanding and what we're seeing from the data, if the stop is longer than 5 or 10 minutes, I forget, then they reset the trip. That said, since we have the device ID, we can actually keep on tracking the vehicle throughout the observed period for which we have the data. So it doesn't really interfere with the analysis.
Great. Another question. Please.
I'm sorry. Yeah, I see a few questions for me, and maybe I can just address them orally rather than typing it out. So a couple from Sarah Hackett. So any timeline on incorporating bus or transit, a CATT Lab. So depending on the data provider that we get the data from, we're kind of setting aside the subset of data that we think is transit related. We can put it on the map. We don't have a tool just yet to ingest and analyze that data, but we're considering it. So we're not abandoning it. It's something that's being considered, but right now an agency hasn't really asked us to pursue that just yet. But that being said, we're starting to look at the quality of the data so that we can support and provide results and visuals that are usable for our clients.
Great.
Another question that I had, if you don't mind, Brendan.
Please.
From Sarah again. She's asking about the software to create the analytics that we have. Is there any other information ingested, and how long have we been using our tool? So our trajectory analytics, so everything essentially that is on our platform that we call RITIS, which is on my last slide here, Regional Integrated Transportation Information System, is created in-house by the CATT Lab. So we're not only, our trajectory analytics tool has been available, I think, for about 2 or 2.5 years now, and we're continually improving it. But before that, the CATT Lab's been around since 2002, in the RITIS platform, I believe, since around 2008 or 9. Everything probe data that you can think of, legacy probe data with traffic message channels. We also work with a lot of agencies to bring in pretty much any data that they have: CCTV feeds, weather information, crash information, signal information. We bring that all together on the one platform for real-time operational decision-making, but most of the data that we're getting, we're archiving, and we've created a suite of tools to analyze that data, which, Sarah, if you want to follow up with me after, I'd be happy to give you a demo of what we do at CATT Lab there. But most of what we do is, developed in-house.
All right. We have an additional question. What tool would best capture vehicles that spending extra time searching for parking in downtown or recreational areas? Do we have any tools on that?
Yeah, so not a CATT Lab, at least not currently. We don't have tools that can directly drill down into that. That being said, it's possible with the data, if you can see sort of a circulating type pattern that you would expect for someone that's looking for parking. It's possible to tease out that information. It would sort of be a cyclic coverage of road segments, and probably with not much time in between them. So that's a good consideration, one that we haven't done yet, but it might be an additional feature that we can think about in the near future.
So I guess a question for all of you working with this data, what sort of privacy issues have you had working with the data sets, and how do you handle those?
Well, I can start. I don't really see any privacy issues here because the data that we get from NITC has been anonymized. So yeah, that's pretty much all I would say. Mark, do you want to add something to it?
Yeah, I mean, that's from the data providers that we work with, it's the similar case. We just get a trip ID with waypoints and with lat long and time. But furthermore, as you can see in our tools, we don't allow people to request data from a specific address or a specific time of day. It's aggregated at the monthly level for the lowest spatial resolution that you can get to is a traffic analysis zone, and for 1 month. So you're at least going to get 4 days of data, just like 1 day of the week, which in our test so far is you can't pick out any one vehicle to identify where that vehicle came from or went to. So that's a sort of an extra layer of we're hoping that's protecting the personal information from the people we're getting this data from, in addition to how it's sent to us from the data providers themselves.
Great. Did you mention how accurate the count data is on local streets?
Well, we take the ATR data, the traffic sensor data, as the ground truth. How accurate it is, we believe it is accurate, but we haven't really checked for it.
Okay. How do you validate trajectories?
Well, we work with what we're given from NITC, so I guess this would be more of a question for them. But looking at all the visuals that, for instance, CET was demonstrating, I mean, they just showed the patterns that we would naturally expect to see. Same goes for the route analysis that Mark was doing. So we have, definitely at CATT Lab, but also internally, we have done quite a bit of analysis and drilled down to, to show different use case scenarios, and it always made sense. So yeah, I guess that would be a way of validating that this data that we're getting is indeed legit.
Okay.
There's a question. Oh, I'm sorry. Go ahead, Seth.
Oh, I was just going to say, when we got our data from INRIX, we did do a few checks just to make sure the data was good and we didn't find errors. One of the things I did was essentially making sure that there weren't like 2 points in a trip that would need to have like an absurd travel time. So I looked, say, if we have a point that, 10 kilometers away for the same device ID, but the timestamp is only 5 seconds, we'd throw it out. So I looked for trips like that, and we didn't find any trips that have those characteristics.
I see another good question from Nikola Mitrovic. So he's asking about the average gap time lapse between 2 waypoints. So here we're working with the 2018 NRIX data, and there the average gap is about 50 seconds, if I recall correctly. So this is where we need to do some of that additional processing, map matching that Mark talked about. As far as I know, I think in 2020, NRIX introduced a new product where they actually do all this map matching for you. So everything is on the road network. I think the sampling rate is actually higher than the 50 seconds. The penetration rates are also much higher than the 3% that we're measuring in 2018. So yeah, I would say that things are improving very, very rapidly on that end.
There's another good question here from Amanda Deering related to the intersection analysis tool. So her question is, does the trajectory data have frequent enough waypoints to get the intersection turning movement detail? Were there any issues with missing waypoints through the intersection? And then how does the tool, sorry, getting cut off. Well, how does the tool go from trajectory data to intersection count level volumes? How was it scaled? So, Amanda, those are all really good questions. So we pre-filter the trips that are eligible to use for the intersection analysis. So the ones that only have very short temporal or very, very high resolution temporal. So the waypoints are only a few seconds apart. Anything more than that, we don't include in the intersection analysis. So in terms of scaling that up, in this particular case, and this is our first launch of this was in Detroit, we had access to intersection count data, so that we were able to link that up and scale it up with the volumes from the sensors at each of these intersections. So that's how we scaled it to represent the full data set there, or estimate of the full data set, I should say.
Great. Any other questions from the audience? All right, well, I think we should wrap it up. We do have, well, all right, we do have a late question. Would any of you like to handle between the vehicle trips and bikes, electric bikes?
Sure. So, well, NRIX provides, so the question is about the classification of vehicles. So what type of vehicle produced each of the NRIX trips that we have in our data set. So as Mark said, NRIX provides rough classification, which is already extremely useful. But say the case that Mel is referring to, it would all fall into the category of vehicles below 14,000 pounds. Now, if you were interested in trying to differentiate between, say, bicycles and vehicles, we have done work on deep learning approaches to infer the mode. So the type of vehicle or the mode that produced individual vehicles. So this is not given to you right away by NRIX, but it can definitely be inferred based on the speeds, accelerations, and other features that we can readily extract from trajectory data using deep learning. So along these lines, we also showed that, for instance, we can differentiate between FHWA classes 2 and 3. So the passenger car and the pickup truck with very high accuracy of nearly 90%, purely based on the features that we extract from the trajectory data. So it's something doable, something that we could certainly do, but it would require additional processes. It wouldn't just be provided to us by NRIX.
Great. Thank you very much, Mark, Nikola, and Seth. Just want to remind everyone, we have a Friday transportation seminar coming up this Friday. Starts at 11:30 a.m. Pacific time. It's going to be on moving toward equitable transit-oriented developments by integrating transit and housing. So please join us for that. There's more information on our NITC website, including more information on this project. So please check that out and join us again for another one of our webinars soon. Thank you.